Hi, my name is Kristen Phillips, and I am doing my final presentation on alternating circuits and looking a little bit at alternating currents as well. So the audience that I kind of geared the information for this presentation are for my high school students. They contain some basic knowledge of imaginary numbers, and then some of them, depending on which class that I might be gearing this presentation towards, do have some knowledge of direct circuits, and they may have been introduced to alternating circuits but may not have dived any deeper into it. So currently, students are familiar with the fact that imaginary numbers are denoted by I, and that I is the square root of -1, and they also have the understanding that I squared is -1. This concept is challenging for students because just like math teachers hear all the time, when are we ever going to use this? When we introduce imaginary numbers, that same question still pops up. If it's imaginary, when am I ever going to be using this? And what I tried to look at a topic to use for this presentation, I wanted to find a topic that they could learn about imaginary numbers or complex numbers, but in another class outside of math. So that's why I dove into alternating circuits. And so as I get into later in this presentation, it talks about thinking about imaginary numbers as an arbitrary thing as opposed to it being really imaginary. And so I stumbled upon a definition that I really thought changed the way students thought about complex numbers. It's a mathematical quantity that represents two dimensions of magnitude and direction. So if we get students to think about complex numbers, including the real part and the imaginary part, and start changing their thinking in terms of two dimensions being magnitude and direction, they might be able to understand that there's so much more to complex numbers than just being a term that they're using to compute. These high school students currently have an understanding with complex numbers being a plus bi, and they understand how to do operations with it. But I think using this definition, it shows them that there's really so much more to it than just those two terms. So alternating currents is an electric current which periodically reverses direction and changes its magnitude continuously throughout time. And so we're going to look at an example with electricity that changes between positive, negative, and the sine wave. When we combine these currents into a new current, if we were to just use real numbers, our calculations would be severely complex. So by allowing us to use complex numbers, we arrive at these calculations becoming a little bit more simplified. Here's an example. So if we were trying to light a incandescent light bulb, we've got current flowing throughout our circuit, and an alternating source might tell us that we can go in either direction. Okay, and then I transform it into a sine wave. We're going to talk more about these sine waves and how that relates to alternating currents here in a moment. So our alternating current circuits, we are ultimately working with voltage, current, and resistance. But with alternating current circuits and how they're different than direct current circuits is that they're not one-dimensional. They contain multi-dimensionals because they start alternating in direction and amplitude. And by the time you throw in frequency and phase shift, there are also two dimensions that you also need to be considered. So we have a lot of things going on in these alternating current circuits, so we need to consider all types of quantities when working with it and performing these calculations. So specifically, imaginary numbers are needed when working with the phase angle, okay? There's a time delay between the voltage and the current, so to offset that, we need to make sure that by using another component, the imaginary numbers, we can work with that time delay. So for example, consider a resistor. When we apply a voltage to a resistor, the current will flow through, which you can calculate that current using Ohm's law. However, if we know the instantaneous voltage, we can derive that current and find the power, which is how much work the electricity is willing to do. When we use complex numbers, we can use that to help us in forming some of these calculations. For direct currents, Ohm's law works. But when we start throwing in capacitors and inductors, With an alternating current, we can't use Ohm's law. So then the use of complex numbers becomes even more crucial. When you're working with a direct current, resistors, the imaginary numbers are 0. So direct currents, imaginary numbers are 0. You can perform your different calculations, which is why we can use Ohm's law. When voltage and current are working together, you can't apply Ohm's law, and that's when imaginary numbers are going to become useful. So for another example, using a capacitor, current only flows when the capacitor is charged or discharged. So you can think of current being kind of relating to the rate of change that the voltage is using and not using that instantaneous voltage. So how can we then represent that instantaneous voltage? If we can't use that instantaneous voltage, how can we then represent this voltage without just using real numbers? That's when complex numbers are needed. So looking at a graph to kind of compare voltage and current, plotting our sine waves. So here we have our voltage is our yellow wave and our current is our green wave here. And you can see from this graph that when my voltage is at a peak, my current is at a minimum or minimal. So how do we compensate for the voltage and the current in one circuit if when my voltage is at a maximum, my current is minimal? That's when we can think back to pre-calculus, and if my students have been introduced to this in pre-calculus, they understand that these sine waves resemble our x and y graph, and it going around a circle, representing a constant rate. That's similar here with our voltage and our current. They're working through a circle, representing, if they were representing a constant rate. So again, it is extremely important that when working with alternating circuits, that we do have those complex numbers available to us to be able to calculate these different circuits that when they are combined, they are more complex. You might not need complex or complex or imaginary numbers when working with direct circuits and when they're not combining. But once you start combining circuits, you need to have another way to be able to calculate these currents. And by using imaginary numbers, that arbitrary term, we are able to do so. So here's a link to some of the resources that I found useful and just diving into the basics of alternating circuits and currents. I did find it kind of rather interesting. It kind of challenged me a little bit to think more about my high school days and learning some about this stuff, but it gave me a better understanding and a better view as to when are we really using imaginary numbers, because a lot of us are using imaginary numbers in everyday lives more than we might think. Thanks.